Okay, so welcome back to. So now we start on determinants in earnest. So far, what we saw was henceforth I'm going to take multilinear maps, and multilinear maps basically having the same n-dimensional space as all of them. So v1 plus v2 plus vn to w. W is going to be the scalars, and whatever n is, v1 plus v2 plus vn will be f to the n. Okay, so we will see that. Except now onwards, we will not talk about multilinear maps on vector spaces. I will do what I did here, which is suppose I have 2 by 2. So I will write like so v1 cross v2. I will take both to be f2. So f2 cross f2 to f. Okay. And actually, strictly speaking, I'm going to do something different. I'm going to do f2 transpose cross f2 transpose to f. So I will treat them right now. I'm writing them here as columns, but I will actually write this as row vectors. And so this is, I'm going to keep calling them as T0 of or T of whatever of the matrix A, and now the B goes here. So these are supposed to stand for the rows of the. If you want, you can just put transposes here. And for the last class, that was fine. For today's class onwards, I will do this. And the reason I'm going to do this is because we are going to see determinants. And traditionally, it is something very odd about how linear algebra is taught. Traditionally, the beginning of the course, solving linear equations, is done via row operations. Row reduced echelon form, row operations, row equivalent, blah, blah, blah. But vectors are written as column vectors. And that sort of is a basic incompatibility which you see here. So for today's class, I will talk about vectors being row vectors because I want to talk about row operations. So we will see that. Okay, so with that background, let us start. So as I said, I will no longer look at multilinear maps as maps of pairs of vectors, but directly as maps where those vectors are the rows of a matrix. Okay. And I'm therefore going to look at maps from matrix spaces. In fact, map from a square matrix to scalars. Okay, so let us continue. So let's see. Last time we saw this. So that's okay. So today, let me just in fact start with yeah. So first of all, let's talk about alternating maps. Okay, so that's the first part of it, alternating maps, and then we will talk about determinants and so on. Okay, so henceforth, let me even fix something. So we work with multilinear maps. Okay, so again, everything is over a field. We work with multilinear maps. Let's see, so T from V. So in fact, so I'm going to say, so here V1 equals V2 equals Vn equals f to the n, and W equals f. So we really just work with scalar valued multilinear maps. T from f to the n cross f to the n cross f to the n. So strictly speaking, in fact, it's f to the n transpose, right? Okay. To f. And so it takes things like, or more generally, or basically, T from f to the n cross n to f. T of u1 transpose, un transpose is a scalar in f. Okay, that's the idea. We will talk about the rows, and this is multilinear in rows. Okay, that's good because we want to do row operations and so on. Okay, so this is the setting. Fine. So this is where we start. So now let me define an alternating map. Okay, or maybe I should say, maybe I should just let me make sure to define this just to be safe. But you already know what this means. So let me just put it here. T is multilinear in the rows, i.e., I just basically this is like a reminder of last time what multilinearity meant, but why? So T is multilinear in the rows, i.e., so given, so given, first of all, fix a column, fix a row, 1 less equals, let's say I fix the ith row, and rows U1 transpose, so let's call them U J transpose for J not equals I. We have the condition, right? We have what condition? We have T naught or T of U1 transpose dot 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 UI minus 1 transpose, and then let's say CU plus C prime U prime transpose transpose. Let's call this V. So I don't have to write prime. CU plus BV transpose. Right? Let's create some space. UI minus 1 transpose, then the UI plus 1 transpose, dot 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 UN transpose. So if I just have the ith coordinate as a linear combination, then you know what it is. It's C times T of U1 transpose, UI minus 1 transpose, U transpose, UI plus 1 transpose till UN transpose, plus D times T of, and I will leave it to you to fill out the rest. I'll just say V transpose here. Okay, so that's literally what multilinearity means. And now for the definition of alternating. So this is literally from last class, so I'm not calling it a fresh definition. Okay, T. Okay, so multilinear in the rows. So that's what it means. And now we say that a multilinear map T is alternating. Actually, a map T from, again, F to the n cross n to F. So it's multilinear in the rows, and now this is going to be alternating in the rows. If basically it says whenever you have whenever you have a matrix with 2 rows equal, the value is 0. In the rows. Okay, maybe I'll just say, in fact, it's multilinear as well. So let's just say that. If one T is multilinear in the rows, and 2, if A in F to the n cross n, if a matrix has 2 equal rows, then T of A equals 0. Remember, it's a scalar, well, it's the 0 scalar. That is the definition of an alternating map, alternating in the rows. Now, the question is, of course, this hardly looks like alternating. It says something is 0. What is alternating order? Alternating typically means if you flip something, you get a sign, you alternate in sign. Okay, it's like somehow odd, even, or -1, -1, +1, -1. That's what alternating means. This is not really saying something. So, well, the alternating part comes from the fact that this implies, and almost in many cases is implied by, if and only if you switch 2 different rows, if you interchange 2 rows of a matrix, then the T value gets a minus sign. That's it. So like A minus B versus B minus A. They are negatives of each other, right? So if you flip A and B, you get negatives. The same thing happens here. That's what an alternating map is. Yeah, but why am I defining it this way? This is slightly more general. And I will tell you right now, I think, right now exactly what that means. But now, so what does it mean to flip 2 different rows of any matrix? That is actually applying a row operation, right? You're actually saying I'm applying the second row operation, E2. So now we go back to our first week of classes and we remind ourselves of the row operation notation and we continue from that. So here is the basic lemma of alternating maps. How alternating in this definition implies the alternating in the row flipping definition. Okay, so recall. In fact, we will need all the three kinds of elementary row operations. On matrices. So let's write them down. One was E1. This is the row operation where you multiply the ith row by a number which is C, which is non-zero. Okay. Then we had E2, which was to just flip, interchange the ith and the jth rows. And then we had E3, which was I. We add a C times the ith row to the jth row. So these were the three different row operations. Right? And what did we know? We had already seen. We know that applying any of these row operations to a matrix is the same thing. So, EI of whatever is here, EI star here, is the same as applying that row operation to the identity matrix and then multiplying it by this matrix. This part we already know. And we have verified it or we have proved it and so on for all types of row operations. For all I. Meaning for all I goes from 1, 2, and 3. Goes from 1 to 3. Okay, so we know this. We will use this. That's why I'm reminding you of these things, the notation, and this basic, very, very important fact. Okay, so now let's see. So now let me write down the lemma, I guess. Yeah, why not? Maybe I should first remind myself to remind you guys of the row operations. So recall. And the fact that the I star of A is the I star of identity times A. Okay, so now the lemma is the following. So let's say the map is alternating, meaning also multilinear. Then it must satisfy that. So let's say, okay, so say T from F to the n cross n to F is obviously, as I said, multilinear and alternating. Okay, I think I know what to do. First of all, this is not an assumption. This is not part one. Let's say this is multilinear. Okay, I'm going to skip the if is because I don't have space. Okay. Now, if P is alternating, then if you apply the second row operation, if you split two rows, then T of E2 I comma j of A equals minus T of A. You just get a minus sign for all A in F to the n cross n and 1 less equals I, not equals j. You could also take I less than j, that doesn't matter. Because the E2 ij and E2 ji are the same. Okay, this is true. Secondly, this is if it is alternating, then this alternating condition happens. Of course, ideally we would like that if alternating condition happens, implies the alternating part. And that is also true, but that needs an extra assumption on the ground field. So this is why we use this as a definition of alternating and then derive the condition that it is alternating. Just like we use the definition for finite dimensionality to be that it has a finite spanning set, not a finite dimension, not a finite basis. And from that we derived all the other conditions that any two bases have the same size and any spanning set can be reduced to a basis and any linearly independent set, so on, right? So we didn't use the actual definition that the word suggests. The same way, the alternating does not suggest this. It suggests this, that you get a minus sign when you switch two rows. But we will use the weaker definition and imply this. And the converse holds. Under one sufficient, we need one condition at least. If 1 plus 1 not equals 0 in the field, it doesn't matter what dimension it is, you need that the characteristic is not 2. Okay, that is the condition. Okay, let's prove the lemma. Let's prove the lemma. Okay, so proof of 1, let's say. Okay, so suppose T is alternating. Okay, fine. So let's write this down. So let's write down the maps. I want to prove this. So let's start with the matrix. Let's say A equals, you again write this down using the rows. And we fix I not equals J. We want to take A in F to the n by n, and for every A and every pair I comma J, we want to prove this. Okay, so what I do is now I define a new matrix C. Define from this data C equals, again I do the same thing. I get U1 transpose. Let's say I take I less than J. It doesn't matter, but I can take I less than J because E2ij and E2ji are the same operation. So it doesn't matter which one I take, right? So I take I less than J, fine. Then I get what? Let's say Ui minus 1 transpose. And now here, instead of saying Ui transpose like here, I say Ui transpose plus Uj transpose. Okay? Maybe I should stop putting these bars. And then I again do the same, Ui plus 1 transpose, so on, until Uj minus 1 transpose. I should shut it off so quickly. And once again in the jth place, I again put Ui transpose plus Uj transpose. Again now Uj plus 1 transpose till Un transpose. So every other row is fine, except I do Ui transpose and Uj transpose in both. Therefore clearly C has two identical rows, so the value at C is 0. Because the two rows are identical. On the other hand, because this is multilinear, you can expand, right? The T of C is equal to, so it's like saying the A plus B times C plus D, right? So it's T of A comma A plus T of A comma B plus T of B comma A plus T of B comma B. That. Okay. On the other hand, but also by multilinearity, we also have T of C equals, let's see, so I will say T of C, which was 0, of course, is T of C1. Let's call it C11 plus T, I'll call it C of T Cij plus T of C, so actually we should start with Cii plus T of Cij plus T of Cji plus T of Cjj. Where, of course, I need to tell you what these four matrices are. So I'll say that on the next board. But you know exactly what they are. They are the ones where you choose the rows only one term at a time. Now I know what to do. I can do this in one row. Where I'll call it CPQ equals U1 transpose Ui minus 1 transpose. Okay, and then I'll call it here UP transpose ui plus 1 transpose, uj minus 1 transpose. So all these rows remain the same. It's only the ith row and the jth row that change. And here I put uq transpose, and then again uj plus 1 transpose, un transpose. For all terms. Right, so for each of those four choices, I can put ui transpose here, I get cii. Ui transpose uj transpose here, cij, and so on. Okay? So in particular, what is cij? I wrote these three matrices, right? What is cij? I should maybe make this. I'll put the where here. Where CPQ equals this. Now what is Ci? So what is Cij? Cij is the matrix where the ith column is ui, ith row, and the jth row is uj. That is exactly the matrix A. So Cij is A. Okay. What is Cji? Cji is where the jth row is ui and the ith row is uj. So it has been interchanged. That means Cji equals the E2 of A. And what can you say about Cii and Cjj? Well, they have Cii has two identical rows, ui transpose, and Cjj has two identical rows, uj transpose to uj transpose. Two rows equal. And this one as well, right? Two rows equal. And now therefore you can just add them. This also has two rows equal. That is why the whole point. That point was that also has two rows equal. So 5 of these terms have two rows equal. By definition of alternating, they are 0. 0 equals 0 plus t of A plus t of E22 of A, E2ij of A, plus t of Cjj, but again that is 0. 0. By definition. Or since t is alternating. Let's say that. That means t of A plus t of this thing is 0, so this thing is minus t of A. Implies, so we have. That is part 1. It's just literally writing down a clever matrix where you have the ith and the jth rows added up together. The second part is the converse. So that is actually, I think, slightly simpler. So let's just say the ith rows and say the ith and the jth rows of A are equal. A, I can even say, let's say A belongs to F to the n cross n. Are equal. Okay. Then it's very simple. What you do is the following. Let's start from T of A. Let's apply that same elementary row operation. What do we get? Since the ith and the jth rows are equal, we get A again. So A equals this thing. Okay? And now we are given this. Now the point is, we are now not given that the map is alternating. We know it is multilinear. And we are given that T of E2 is minus, we are given this condition. So I can use that here. So I get T of A equals minus T of A. I can add T of A to both sides. I get 1 plus 1 times T of A, or 2 times T of A is 0. T of A is a scalar. So I can say T of A plus T of A. And now I can take T of A common and get 1 plus 1. But now since 1 plus 1 is not 0 in the field, it has a multiplicative inverse in the field. Every non-zero element of a field has a multiplicative inverse. I multiply by that inverse on both sides. So that's how you prove that. Yeah, that T of A is 0. Okay, great. So that is. Okay, perfect. Very interesting. So now, Okay, so we talked about alternating maps. So again, let me remind you of the one alternating map I can tell you about in 2 by 2 matrices. So by the way, in 1 by 1 matrices, every linear map is alternating because you can never switch anything. Right? So by vacuousness, so maybe I should say a remark. For n equals 1, every map is alternating, every linear map is alternating. So 1 second, I'll write that down here. Okay. So multilinear just becomes linear because there is only one term. So f to the 1 cross 1 is just f is alternating. N equals 2. I'll just give you an example of an alternating map. The map T of A, B, C, D is obvious, is alpha times AD minus BC. Well, let's call this T alpha. It depends on alpha. Alpha is a scalar. Is alternating. So alternating automatically means multilinear. For every scalar alpha in the field. Okay, so that is the point of alternating. So now the point is what we are going to say about a determinant. It is one of these maps. It is one of these maps for a very specific choice of alpha. And so this choosing an alpha basically is something like, it's in probability theory you would call it normalizing. Even in Gram-Schmidt, you would say you normalize a vector so that its modulus its length is 1. Why should the length be 1? You can make it some specified length. But that's the point of normalizing. You make something 1 or you make something 5. You choose a particular scalar and fix it there. The scalar we will choose is alpha equals 1, and the reason we will choose it so that the identity matrix has this value equal to 1 times 1 minus 0 times 0, which is 1. So I want the identity matrix to have value 1, and so I choose alpha to be 1, and T1 is going to be my special multilinear alternating map. Okay? So, and that special map is called a determinant. So now let's write down, I think, the definition. Yeah, so here we go. Now we can write down these preliminaries. Okay. So fix a field and whatever. So f is a field, n is an integer. A determinant is literally an alternating, so multilinear map, which satisfies that the identity goes to 1. That is it. Okay. So a determinant on f to the n cross n. A determinant is a multilinear alternating map okay, yes. T from f to the n cross n to f such that T of the identity is 1. That is it. That's a determinant map. The amazing thing is that no matter what field you choose, no matter what dimension you choose, there is only one determinant map, and there is one, always. So this thing about expanding, blah, 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 that is if and only if the map is expanding along a row or along a column, they all give you the same answer. Why? Because they are all one and the same, the uniqueness part. So that's the point. It's if and only if it's a multilinear alternating map. And each of them is, therefore, they are all the same map. So that's the amazing thing about determinants, and we will start proving it. I don't know if we will be able to prove the existence of the determinant, but modulo the existence, we will prove everything else. Okay, so let's see. So let's start with all the nice and easy properties to prove. Well, easy may not be quite the answer, but yeah. Let's start with the nice and most attractive properties. And the last part is the existence part, which is also the computational definition of the determinant, expanding along some row or some column. So that is the more boring part. But anyway, we'll get there. So first, let's start from determinants and elementary row operations. Yeah. Lemma. And elementary row operations. So this lemma is going to connect these two things, okay? Let's see, what do I want to say? Yeah, so suppose we have it, say that from f to the n cross n to f is a determinant. So suppose a determinant exists, which, as I said, we will prove next time that it does exist. Suppose that is a determinant, then I want to say that, okay. Then that E1 of C, sorry, I comma C of A is C times that A. If you rescale a row, you get this. If you flip two rows, you get a minus sign. That we already saw. And if you add a multiple of a row to another row, you don't change the determinant. These are the three properties of how row operations affect the determinant. The first one is that rescaling a row rescales the determinant, flipping two rows negatives the determinant, or negates, I don't know, and adding some multiple of a row to another does not alter the determinant. Okay, so now how do we prove this? Let's see. So I mean, this is sort of this is straightforward, right? So proof one, I mean, it is multilinear. So in particular, it's linear in the rows, right? So if you multiply a row, then the linear constant comes up. From definition, one follows from definition, follows from multilinearity. Two follows from the above lemma. Sorry, this was a lemma. Okay, this was maybe this. So let's call this lemma 1, and this let's call this lemma 2. And 3 also follows, right? Well, again, because it's linear, so I times. So if you do something like this, right? Everything else is the same. This is the j, I'm adding it to the j's column, so uj plus cui, but this is equal to the uj part, transpose, everything is transposed, plus c times, this is all linearity properties, this is ui, transpose, but also this is the jth row, and the ith row also has a ui transpose. So you have two different rows with the same vector in them, that's why this is 0. So it's just back to the original matrix, determinant of the original matrix. In this, there's really nothing to prove. This is obvious. The corollary we derive from this is going to be interesting. So the point is the following. Now let me remind you of what we knew earlier, right? We have seen earlier, I just wrote down that thing in the box which I erased. That acting on some matrix by elementary row operation is the same as saying act on the identity by that operation and then multiply by this matrix. Right? So what happens? Let's look at the what happens to the determinant of the identity when we act on it by this row operation. So on the other hand, so this is all fine. On the other hand, what do we have? Let's look at, let's say, E1IC of identity. Let's say determinant what is the determinant of, what is the E1IC? It is 1 1 1 1 1. There's a C and then 1 1 1 1. And this is in the I comma I entry. But now it is multilinear in the rows, therefore I can take the C outside. This is C times the determinant of what? I just get all ones. But that ones is the identity matrix. So determinant of identity by definition is 1, so this is just C. Which means this thing here is the determinant of this elementary matrix. Interesting, right? Second, similarly, the determinant of E2 of identity is the determinant of the matrix where everything is ones except for something here, which is this is 1 and this is 1. Again, inside it you get ones, but these two are swapped. But that is the same as saying I've just swapped these two rows. And because my map is multilinear and alternating, I know that that of course gives you -1. The map is alternating. So this is our lemma 1, right? And then the third one, similarly, you can check just by this kind of calculation. By that kind of a calculation, determinant of E3 ICJ identity is just 1. Okay, so you can check all these out. Therefore, I can say something better now. Maybe I'll use a different pen, a different color. So maybe now I can say something better, which is that I can say, look at the determinant of, look at this determinant. Maybe I'll just say it here. So, thus, these imply this is my corollary. If E is an elementary matrix, EI star of identity. So basically, an elementary matrix is the matrix you get when you take some row, elementary row operation and apply it to the identity matrix. Is an elementary matrix, is an elementary row matrix, I guess. Let's say this is n cross n. This is identity n. Okay. Then det of E times A. E times A is what? This is this times identity. That is the same as saying it is just applying a row operation to a matrix. Det of E times A is det E, either C or -1 or +1. Either C or -1 or +1. Is det of E times det of A. Oops. So this is immediate. This is the, look at the lemma. This we already know that this is that this is E times A. This is that of E times A, that of E times A, that of E times A. On the other hand, you know that this is C times that A, -1 times that A, +1 times that A. That we have already proved in the lemma. Although it's obvious. But now I know that det of E is C -1 or +1. Therefore, I just get this for free. And this is important. So all you see already is the determinant seems to be multiplicative. If I have two matrices and one of them is elementary, of course, then I see the first one, then the determinant seems to multiply. You can obviously ask, is this true more generally? For which square matrices of the same size can you say the determinant of AB is or B times A is determinant of B times determinant of A, right? Or A times B is that A dash. And I think I can, yeah. So now I think we can write down the main theorem of this lecture. And as I said, I'm not sure I can finish proving it. I'll prove everything except the uniqueness, sorry, the existence of determinants in this lecture, and the uniqueness part we will do next time. So this is so. We proved a couple of lemmas and one corollary about determinants. Interesting. We will see what happens. So main theorem. So theorem on determinants. Okay, so let's say I should fix a field but not dimensions. Because the existence will be by induction on dimension. Okay, step one. This is the hardest part of all, so I will not prove it. But yeah. For all n bigger equals 1, a determinant function exists and is unique. On the n cross n square matrices. This is the hard part. Is 2 the multiplicative part? No. The determinant function, well, it's unique, right? So I can now tell you about the determinant function. The determinant is non-zero if and only if A is invertible. And the third is that the determinant is actually multiplicative for all matrices. For all AB in F to the n cross n. That is the main theorem. Okay, great. So now let's do this. Yeah. Okay, so proof, and as I said, in the proof throughout, I will assume the determinant exists. So we can't prove stuff about determinants unless they exist. So assuming it exists, which I will prove next time without using the rest of the stuff, let me prove the rest of the stuff. So let's start with 2. The determinant is non-zero if and only if A is invertible. Or do I want to do the uniqueness first? Uniqueness. Using the corollary, I can do the uniqueness first. Yes. I should do the uniqueness first. Why not? Oh. Wait a minute. So okay. Okay, no, I should do uniqueness after here. Okay, let's start with 2, and then I'll get to 3, which is the uniqueness part. Okay, so now this one, right? So okay, let's do the following. Let's just say A is not invertible. We'll do both sides. Either if A is not invertible, the determinant is 0. If A is invertible, the determinant is not 0. Okay, now as I've already talked to, we have seen not infinitely many, but plenty of different characterizations of non-invertible or invertible matrices. One of them is that the row space is not the full space, right? Or the row rank is less than n, the column rank is less than n. So let's say it implies the row space of it. So they are not, if they were a basis, then the row space would be full. If there are n of them, if they span the whole space, then the row space would be all of Fn. So they don't span it. But in a finite dimensional space, they don't span the Fn only if they are not linearly independent, because they are all in Fn. We have seen all of this. Are linearly dependent. I.e., there exists I naught less equals n such that, let's give this, I should have said the A. Let's say A equals, again, the usual U1 transpose, dot 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 UN transpose. Is not invertible. Okay, then the rows of A are linearly dependent, i.e., there exists I naught such that UI naught transpose, the row, is a linear combination of I naught equals I naught, Ci UI transpose. For some scalars, yeah. This is a linear combination. That is why the rows are not linearly independent. They are linearly dependent. Okay, but now you see I can write this down as, but now the determinant is multilinear, so I can write down, so it implies det of A is det of whatever this is, and then U I naught transpose, and then whatever this is, the rest of the rows. But UI naught is transpose is this thing, and it is multilinear. This is summation I naught equals I naught, Ci, and then dot 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 UI transpose dot dot dot. And notice that the column, the row number here is I naught. It is not I, it is I naught. But you see, I is not equal to I naught, and in some other, the ith row, you also have a UI transpose. And that UI transpose never changed. It is only these guys that keep changing. And so for every I, you look at the ith row, you look at the I naught row, and they have the same vector. Therefore, because two rows are equal, the determinant is 0, because it is alternating. Sorry, I should have said summation Ci times det of this. Yeah, and now det of this is 0 because it's alternating. So necessarily, if a determinant exists and the matrix is not invertible, then the determinant of that matrix must be 0. Okay, there are no two ways about it. So when I said that there is a uniqueness part, well, that part is just uniquely 0. No matter what you do, it has to be 0. The question about uniqueness really happens if the matrix is invertible. Then what happens, right? So let's first of all, let's show that the determinant is non-zero. This was if, so say A is not invertible. If instead A is invertible, if instead A is invertible, then what do you do? Well, then we already also know another characterization, which is that it is a product of elementary matrices. Write A equals E1, E2, En, where each EI is elementary. Each EI is an elementary matrix. But then we know that the determinant of each EI is non-zero. The determinant of each EI is either C if, or -1 or 1, where C is non-zero. And because for the first row operation, first kind of row operation, you rescale the row by a non-zero constant C. So C is non-zero. Or you flip two rows, you rescale by 1 the determinant. So that 1 was the -1 was the det of E of identity, which is these matrices. Or you don't change the determinant, so the determinant was 1 of the elementary matrix. Okay, but then what does that mean? Now, okay, first of all, you know this. But also, we also know also by the corollary that A is E1 times E2 times dot dot dot. And we know that elementary matrix times anything, the determinants multiply. That was the corollary. So det A is det E1 times det of E2, E3, En. So again, let me write E2 times E3, En. Again, I get this is det E1 times det E2 times det of the rest. E3, E4, E3, and you can keep going, right? And at each step I take out one of the E's, put a determinant, and keep going. And so eventually I get that it's the product of the determinants. But each of those determinants was non-zero in the field. Therefore, this is the product is non-zero. And so that's what we wanted to prove. If A is singular, then the determinant is 0, must be 0. If A is invertible or non-singular, the determinant is non-zero. That's the proof of part 2. Now let's do 1A, 1B uniqueness. It's basically the same thing, right? So, what is the uniqueness part? So maybe I should switch pens, switch colors. The determinant, if it exists, must be unique. Well, if it exists, the determinant has to take non-invertible matrices to 0. The question really is what happens to invertible matrices. So first of all, let me write down the lemma. Actually, first let me write down the non-invertible matrices go to 0. Okay, so since that exists, or if that exists, so as I always say that exists, then det of A is 0 if, or for all A non-invertible. Okay, what happens if A is invertible? That is unique. There are no two values that it can get. There is no two ways about it. That value is always 0. So the question is now, why is the value at an invertible matrix, the non-singular matrix, also unique? That is the key question. And for that, I need a small lemma, which is, it's very simple really, but I'll just say it. Oh, okay. Lemma. If E is an elementary matrix, look at the inverse, right? The inverse of an elementary matrix is also elementary. If you multiply a row by C, the inverse multiplies the row by C inverse. If you flip two rows, that is its own inverse. And if you add C times some row, then you can add minus C times some row, that is the inverse. Basically, the operation that undoes the row operation. Det of E inverse is, first take the determinant of E and then take the inverse in the field. So take the reciprocal in the field versus take the inverse of the matrix and then take the determinant. They have to be equal. And that proof is very easy. The proof is by direct verification. Check in all three cases. Right? In the third case, for instance, the third row operation, the E and E, if E is of the third row operation kind, then so is E inverse. And for all matrices, elementary matrices of the third kind, the determinant is 1, as we already verified somewhere here. Right? So therefore, 1 inverse is 1, that's obvious. -1 inverse is -1, and C inverse is C inverse. Okay, great. So now I have this, right? So now let me, with this, do the uniqueness. Sorry, 1 second. It's obvious for A equals E, which is all that we need. Okay, so now let's continue. So this lemma is going to be very useful to prove uniqueness. Okay, it's also going to be, yeah, let's prove uniqueness. So now suppose, so what happens now, right? So, so determinant is equal to 0, fine. Now over here, what we said was the determinant of A has to be equal to the product of the determinants of EIs whenever A equals the product of EIs. That is what it is, right? So now, next. So now coming back to the proof. Say determinant exists, then delta equals 0 when A is non-invertible. Say A is invertible now. Okay. Okay. Actually, before that, right? Maybe I should call this bullet point 1. So bullet point 2 is if E is an elementary matrix, then the determinant is uniquely defined. So first, before looking at the general invertible matrix, let's look at elementary matrices, right? Again, why is it unique? Because, yeah. So say A equals E is an elementary matrix. We just saw above why it is unique, right? Because we computed the determinants of those. Just by multilinearity, if I have 1, 1, 1, C, 1, 1, 1, it does in the first kind, the C comes out by linearity, and I get identity matrix, so I get C. So for those matrices, the determinant is unique and it's defined. We saw above, we computed above. After lemma 2, right? Before the corollary and after lemma 2, the unique values of the determinant. Regardless if it's of the first kind, the second kind, or the third kind, we computed that unique value of the determinant of E just after lemma 2. So for them, it's unique as well. And now, the determinant of anything else, a general non-singular matrix, I will write this down using the fact that an invertible matrix is a product of elementary matrices, right? So I'm going to do that. I'm going to prove it's obvious what that value must be. It's mentioned here, but let me prove that it is unique in the sense that it's well defined as well. So okay, now take any general invertible matrix A, be any invertible matrix. Any invertible matrix. Okay, and write down so A equals E1 EM, where all EI are elementary. Okay, great. Then the determinant equals the product. Then we saw above. that the determinant must be equal to the product, so that value is unique as well. Is uniquely determined. I just skipped again. Is uniquely determined. From the EIs, from the decomposition. A equals E1 equal EI. So the moment I write my matrix A in this fashion, my determinant value is uniquely determined. But there might be a source of confusion here. What if I can write A in two different ways as a product of elementary matrices? Then on the one hand, I would get the product of the determinants of the first set of elementary matrices, but also on the other hand of the other set. Is there a guarantee? What is the guarantee that these two products are the same number? Okay, that may be a potential cause of confusion, and so let's prove that that has to be the same number. Regardless of what decomposition I take, I get the same number. Okay, so let's write that down. Now the playlist, this doesn't depend on the choice of the matrices. Right? Unique given the EIs. Okay, so now here is where I'm going to use the lemma again. Okay, so now say A equals E1 prime, EK prime as well. With all, again, the same thing, EJ prime elementary. Implies that the determinant of A is the product over J goes from 1 to K, det E prime J. What is the guarantee that this and this are equal? So for that, I do the following. Note that, so why does this equal that? The question is really that, right? Why is that? Why are these two products equal, and therefore A is uniquely, det A is uniquely determined? So then the definition of det A could be, for instance, that this is the product of the dets of the elementary matrices for whatever choice of decomposition as a product that you choose. Okay, so why is this unique? Why does it equal that? Okay, fine. Let us see why. I will need this, so probably I should keep it. Okay. So because A is equal to these two things, since E1 equal M equals A equals E1 prime, EM prime, EK prime. Very good. Hence A inverse A equals identity gives. So write down that A is invertible. Remember, so A inverse A is identity. This yields the following equality. Let's take the inverse of this. So this inverse times that. Okay? So what do we get? We get, what is the inverse of a product? You have to take the inverses in the opposite order. This is what you get. So you have two matrices which are equal. And notice that every one of these, the inverse of an elementary matrix is an elementary matrix. So each of these guys are all elementary. Row, matrices, right? All of these guys. So now let me take the determinants of both sides. Taking that, when I take the determinant, okay, I think I should switch pens again. You get det of EM inverse sorry. Det of EM inverse dot E1 inverse E prime 1 dot E prime K is det of identity, which is 1. But again, each of these is elementary, so by the corollary, this is det of EM inverse times det of the rest. EM minus 1 inverse dot E1 inverse E prime 1 dot E prime K. But again, by the corollary, I can take this part outside and this part outside, and I can keep going. And then similarly, each of these is elementary, so I can take one at a time outside. So I just do dot corollary. Everything is from corollary. Dot equals, and so I get the product of det of EI inverse times the product of the det of EJ prime. And this product equals 1. But also, I saw this thing by the lemma. Now here is where I use the small lemma or the claim or whatever I have. The det of EI inverse is the det of EI times inverse, not times inverse. Times the product of det EJ. Equals product I goes from 1 to m. The scalar det AI inverse, and then times j goes from 1 to k. And this whole product equals this, equals this, equals this, equals this, equals this, equals 1. And now we are done. Right? Take this inverse, this is the reciprocal of a product, take that scalar to the other side, you get this product equals this product. Clearing denominators in some sense. And this proves uniqueness. And the determinant is uniquely defined to be the product of the det of the elementary matrices, or this equals that value. No matter how you decompose it as a product of elementary matrices, you get the same value. Okay, so that proves part 1b, which is uniqueness. We've already shown part 2. And now let's prove part 3, which is that it's multiplicative. And then if we have time, which I don't think we will, well, we'll have some time. And then I will get towards existence. So I'll say a little bit about existence today, and then we will stop. Okay, so let's see. So now 1b is done, uniqueness. Part 3 is existence, sorry, multiplicativity. The determinant is multiplicative. So again, I'm given A and B in f to the n cross n. I want to prove that the determinant of A times B is det A times det B. The first case is when A is not invertible. Again. If A is not invertible, then A transpose is not invertible. Which is the same as saying that there exists a non-zero vector U such that A transpose times U is 0. I'm using A transpose times U instead of A times U. for a very simple reason. I'll show you. And this implies, this is not if and only if, of course, B transpose A transpose times U is also equal to 0 because it's just B transpose times 0, which is 0. But now you see U is non-zero. So that means that this matrix itself is also not invertible. That's the criteria. That is this equivalence applied now to B transpose A transpose. So now I can again say if and only if B transpose A transpose is not invertible. I mean, this is all a fancy way of, I'm just trying to prove that if A is not invertible, then AB is not invertible. Well, now what is the transpose of this? It is precisely AB. So the whole entire rigmarole here is just to say that if A is not invertible, then A times B is not invertible. Probably there's a different way easier way of seeing this, but this is for me the most obvious way. Now the point is, once you have this, then we are done. Why is the determinant multiplicative? Well, if a matrix is not invertible, we know that the value of the determinant is 0. So det of AB must be 0. Det A is 0, and times whatever you put, det B is 0. So det AB equals 0, and det A times det B is also 0. Because as we proved, or as we had in the very first lecture or very first homework, 0 times anything is 0. We've already seen that. Or 0 times, sorry, I don't need to say that anymore. So that's therefore, so both sides are equal, so we are done. Instead, now suppose A is invertible. And then the argument is already done like 3 times in this proof already, in this proof of this theorem. Okay. If instead A is invertible, if instead A is invertible, then you will do the same thing. Write A as a product of elementary matrices. And now what do you do? Now we have to buy the corollary. The det of AB is det E1, E2, EMB. Let's call this E2, EMB. So again I say, look, it's E1 times this, so it's det E1 times that. And then again it is E2 times some the rest, so it's det E1 times det E2 times the rest, and so on. So keep going. So you get the product of det EI times det B. But already we have seen above that if A is equal to, that was the whole point of that uniqueness proof. If A is equal to E1 into EM, then this is precisely det A. From above. Right, so we've seen earlier in this very proof that det A is equal to this one. So det A times B is det A times det B. So it's just 2 different cases. One is when A is invertible and one is when A is not invertible. So that's the end of part 3. So all that remains in this main theorem is to prove part 1, which is unique, which is existence. So remains to show. And in fact, we assume that the determinant exists to prove all this. So we can't use any of this to prove that the determinant exists. Once it exists, it must be unique, etc., 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 blah, blah, blah. But does it exist? So I just need to produce for you one function of the matrices, which is multilinear in the rows, which is alternating in the rows, and which takes the identity matrix to 1. Okay. I just need to produce one function for you. The moment I do that, it's a determinant, therefore it exists, therefore everything else goes. And the way we will produce this function is the only way that I know how to produce functions and the only way that you know how to produce functions. Right? Expand along some row. Actually, no. Sorry. Okay. That is a trap. Do not expand along some row. We are using the linearity in the rows. You cannot tamper with that. Expand along some column. That is what we will do. So the idea will be we will say that the following, all of those possible candidates, expand along the first column or the second column or the third column. All of these are valid determinant functions for every single dimension. And this is where I am going to use induction on the dimension. So far I have not used anything. So far I fixed a dimension and work with it. But now to prove the existence, we will need induction on the dimension. Okay, so let me start. So let me start you off on the determinant existence proof. I'll probably cover 2 boards and then I will stop, and then we will just resume that in the next lecture. So I will remind you of this and then resume in the next lecture. Okay, so to prove existence, okay, so yeah, so proof of existence, right? So for all n bigger equals 1, I want to prove the existence. Induction on n. So base case, let me just do n equals 1 and n equals 2. In n equals 1, I just, alternating doesn't make any sense because you can never swap 2 things. So vacuously everything is alternating. So it's just, and multilinear just means linear. So determinant is just a linear map that takes 1 at 1. Is any linear map sending the identity matrix, which is just 1 to 1. But then we are done. So det of A. So remember, A is like a 1 by 1 matrix. So det of this 1 by 1 matrix is just det of A. Is A, but it's linear. So linear now I use here. A times det of 1. Identity I use here is A times 1, which is A. So this is a linear, this is a determinant function. This is a valid determinant function. It is clearly linear and it's clearly sending 1 to 1, and there is nothing about alternating. So this satisfies the axioms of a determinant. The properties or axioms of a det function. And of a determinant function. N equals 1. N equals 2, I will leave it to you to check. Everybody should check this once in their life, I guess, that the following is indeed a valid determinant function. The following satisfies the same properties and therefore is a determinant. The function, and you all know what the function is. Det of A, B, C, D equals AD minus BC. Check. I guess everybody should check this once in their life. Well, not everybody. Every student of linear algebra should check this once in their life. Well, why don't you check it once in your life? Check that this does satisfy multilinearity and alternatingness, and identity goes to 1. These are all obvious checks and nothing big. Now for the third, for the induction step, this is where we are going to use the definitions. I want to define it today, and then I want to again tell you the definition next week, because then at least you will have seen this and it will sink in. Okay, so definition. So for the induction step now, I'm going to stop and take 1 minute. So induction step. Say n bigger equals 3, maybe even n bigger equals 2 will work, either way. In n bigger equals 2, if n equals 2, then you just get this formula. There's nothing, you can verify that directly. And that exists on f to the n minus 1 cross n minus 1, right? On the smaller size matrices. Okay, now I'm going to define the following. So now here are a couple of definitions. One, given the matrix f to the n cross n and indices I and j, I'm just defining a submatrix. Let aij denote the submatrix, where you first of all say that the size is 1 smaller, denote the submatrix. Obtained by deleting the ith row and the jth column from A. So I'm just defining these submatrices. The determinants of these submatrices are called minors, but these are called submatrices. Okay. Second, and now this is the key definition, I will expand along the jth column. So for j, for 1 that's equals j that's equals n, define bj to be a map from matrices to scalars. Remember, I'm trying to come up with the definition of determinant, right? This is my definition via dj of A is defined to be summation. So j is fixed, I goes from 1 to n, -1 to the I plus j. And -1 makes sense in any field, so you can take powers of this. And then remember I said that the determinant exists here. I fix it. Fix such a determinant. So you have fixed a det function on the n minus 1 part. I look at det of aij. For every j, I define this. This is basically exactly expanding along the jth column. So that's what we are doing. Right? The claim, and this is where we stop. Perfect spacing. dj is a determinant function. So it is multilinear, it is alternating, and it takes the identity to 1. Is a valid determinant function, meaning it satisfies the axioms of 1. I won't write that again, so I'll just say is a valid determinant on f to the n cross n. That is the claim. So we will start next time by proving it, and that will finish the proof of the existence and uniqueness theorem for determinants. But so that's the idea, is everything else sort of is very nice and easy to prove. Once you understand that the determinant exists, once you assume that, then everything is nice and easy to prove. But how do you prove the determinant exists? So first of all, for n equals 1, this is clear. Just take this. This satisfies the axioms. It is a unique thing that can satisfy the axioms, but the uniqueness was anyway fine from assuming existence. So that was fine. n equals 2, you can check that this also satisfies the axioms. And now the interesting thing is for general, and when I define this map, I also allowed n to be 2. Well, take D1 and D2 for n equals 2 and check that they both equal exactly this map here. So it doesn't matter if you use D1 or D2. You directly see the uniqueness from here, from this explicit formula. This has to be both of them. Because as I said, the determinant is unique. If you try and expand it out, you will see that it is actually the case. D1 of A is AD minus BC and D2 of A is AD minus BC when n equals 2. Okay, so the reason that that formula is fine, no more, no less than any other definition of determinant like this one, is that they are all the same because they have to be the same. It is a unique formula. There is a unique function. So n equals 2 is fine. For general n, we assume that the determinant exists for a smaller dimension and use it to recursively or inductively define the determinant for a larger dimension by expanding across any column. And the claim is now that this formula will satisfy the axioms of a determinant, meaning it's multilinear, it is alternating, and it takes identity to 1. I'll remind you of all of these two boards again next time, and we will start from there. Okay, let us stop.